Oh, that's so weird. And I'm very confused about it because I checked it over the break, and it doesn't make sense. Let me look at it. Yeah, that's very strange. I remember you emailed and I checked, and it showed it correctly on my end.
Yesterday, I just looked at it. And went to class. You know what we had? We had the drinking break.
All right, folks, I think everybody's back. Come on back, folks. All right, we have 3 problems remaining, and these last 3 problems are about distance equals rate times time. I'm thinking that you've all seen this formula before, D equals RT. What does D equals RT stand for?
Distance, rate, and time.
Yeah, distance, rate, and time. Now, this particular formula makes a lot of sense, especially if you think about driving in your car on the road. So, for instance, if you're going, let's say 50 miles per hour for 2 hours, how far will you have gone? You're going 50 miles per hour, and you're driving for 2 hours. Yeah, so you've gone 100 miles. And I hope that just also makes just good intuitive sense. That if you take the rate that you're going, so you're literally stating a fact that I'm going 50 miles in 1 hour. And then if you go for 2 hours, then you're doing 50 miles for the first hour, 50 miles for the second hour. And so indeed, you've gone 100 miles. So we have this nice formula, D equals RT. And what I'd like everybody to do is just start by writing down D equals RT. But I'd like to show you that you can manipulate this equation a little bit. And let's say, instead of writing D equals RT, write down RT equals D. We can solve for R if we want to. Like instead of having D all by itself, we could get R by itself. So R is being multiplied by T. How do you get rid of the T? Divide it off. So now we have another formula which states that rate is equal to distance over time. This is not the common way of looking at the formula. Most people say the formula D equals RT. But you could say R equals D over T. And even though this formula is not the traditional way of saying it, this actually makes a lot of sense because let's say you're talking again about 25 miles per hour. That's the rate, 25 miles per hour. Then you're literally saying 25 miles per hour. So this formula makes sense too, that if you're talking about a rate like 25 miles per hour, it's literally 25 miles per 1 hour. So this formula makes sense even though we don't often see it. Okay, one more time, do it again. This time solve for T. RT equals D. We'd like to solve for T and get T by itself. So T is being multiplied by R, so you would divide by R. So now we have the formula T equals D over R. Now that indeed might seem pretty strange. It still makes sense though. Like for instance, how long would it take you to drive a distance of 100 miles if you're going 50 miles per hour? To use the same question that I already did, how long would it take you to drive 100 miles if you're going 50 miles per hour? 2. And so dividing 100 by the 50 gives you the 2. So we have these different options, and I'm just going to go ahead and write them down at the top of my page here. So either D equals RT, or I could use R equals D over T, or I could use T equals D over R. They are all, in fact, the same formula. They're all expressing different relationships between distance, rate, and time. So, oh, I'm sorry, I'm on the wrong screen. So let's start by talking about Chuck and Dana, number 75. Chuck and Dana. This sounds like a trick question. I don't think Chuck and Dana would be friends. I'm just kidding. I just like to play around. Okay, so Chuck and Dana, they agreed to meet in Chicago for the weekend. So Chuck, he travels 114 miles to get to Chicago in the same amount of time that Dana travels 99 miles. So what does that tell us? Like, here's Chicago, and Chuck has to go 114 miles to get there. So this is Chicago, this is Chuck. And then here's Dana. She only has to go 99 miles to get to Chicago. But they do it in the same amount of time. What does that tell you about which one had to go faster? Yeah, Chuck has to go faster. Does that make sense? If they're both taking the same amount of time, but Chuck manages to travel 114 miles and Dana only travels 99 miles, Chuck is definitely going faster than Dana to get there. Okay, so let's keep reading the problem. Chuck and Dana agree to meet in Chicago for the weekend. Chuck travels 114 miles in the same time that Dana travels the 99 miles. If Chuck's rate of travel is 5 miles per hour more than Dana's. Okay, well, that's good. That's what we thought. We thought he had to go faster, and apparently they're saying that his speed is 5 more than Dana's. Well, what's Dana's speed? We don't know. So what should we call it? X. Now, since we're talking about speed, which letter are we talking about? Rate. So we might as well, instead of using X, let's use R. So we're going to say over here that this is Dana's distance, and her rate, we'll go ahead and say, well, her speed, we'll go ahead and say that her speed is R. Whereas what's his speed? R plus 5. Yeah, so his speed is R plus 5. So this is what we have so far. We've got Chuck going a distance of 114 miles. We've got Dana going a distance of 99 miles. They're both going to Chicago. Dana's speed is merely R miles per hour, and Chuck's speed is R plus 5 miles per hour. I'm just kind of making a drawing here to kind of capture all the information. So let's see, do we have all the information? Chuck and Dana agree to go to Chicago. Chuck travels 114 miles in the same time that Dana travels 99 miles. Chuck's rate of travel is 5 miles per hour more than Dana's. And they travel the same length of time. At what speed does Chuck travel? So what are we trying to solve for? Yeah, we want to solve for Chuck's speed. Now, notice in the problem they told us a fact twice. They said that Chuck and Dana travel for the same time, so they're in the air for the same amount of time. And then later they said again they traveled the same length of time. So what I know for sure is that the amount of time that they spent in the air was the same. So that's the fundamental fact that we're going to use to start this problem. We're going to say that the time for Chuck is equal to the time for Dana, the time in the air. And I'm using a capital T with a little subscript C for Chuck, and a capital T with a little subscript D for Dana. So the thing that we know for sure is that Chuck's time in the air is equal to Dana's time in the air. So that's the starting point of us solving this problem. Okay, now do we have a formula for T? Yeah, we do. We've got this formula. And so what we're going to do now is write down Chuck's formula and Dana's formula in terms of D over R. So now what we're going to say is that for Chuck, Chuck's distance divided by Chuck's rate, so on R sub C, should be equal to Dana's distance divided by Dana's rate. And again, I'm just using subscripts to keep us focused on the fact that here I'm talking about Chuck's time, and time is equal to D over R, and this is Dana's time, and Dana's time is equal to D over R as well. I suppose instead of subscripts, if we wanted to, we could have just written Chuck on the left and Dana on the right to keep us focused on the fact that I'm putting Chuck's information on the left and Dana's information on the right. Okay, so what was Chuck's distance? 114. And what was Chuck's rate? R plus 5. And now what was Dana's distance? 99. And what was Dana's rate? Yeah, R. Okay, well that's it. That's the setup of the problem. We now just have a proportion, we can cross multiply, and we can solve. the key was noticing that their time was the same. And so we were able to say that his time equals her time. And since we had a formula for time, which is D over R, we got to plug in all the information for them for D over R, and now we just have a proportion and we can solve it. Now, I suppose we could multiply all the way through by the common denominator, but I think it would be easier just to cross multiply. I think that would be the fastest solution. So let's try cross multiplying. Remember to wrap parentheses around your R plus 5 and your R first. And so we multiply, we cross multiply, and what do we have? Now, 144R equals 99 times R plus 5.
114.
Oh, 114, thank you. Again, notice the theme of this chapter is we're looking at rational expressions. So this is a rational expression using D over R. And yet, the first thing we do is just eliminate the denominators so we don't actually have denominators, and we just have a normal equation to solve. So let's distribute. So we have the 114R equals 99R plus 185, thank you. And then subtracting the 99R, that gives us 15R equals 495. And if we divide by 15, what do we get? What is it? 33? Really? That's it? Just 33?
Well, we need to add 5 to it.
Well, that's true. So 495 divided by 15. Okay, it's 33. So what does R represent? Dana's speed. So Dana's the one who is going 33, presumably miles per hour. We're just assuming it's miles per hour because they're doing it in miles. So it's probably miles per hour. So Dana's speed is 33 miles per hour. Whereas Chuck's speed is what? 38, because there's 5 more than Dana's. So Chuck's speed is 38 miles per hour. Now, my goodness, folks, this begs the question, were they traveling by air? Definitely not. So how were they traveling? Maybe by car. Do cars really go 33 and 38 miles per hour on their way to Chicago?
Bicycle.
I mean, maybe they're on a bicycle, but that was a very fast sprint on a bicycle. Maybe it was on a bus, or maybe since it's Chicago, it could have been a moped or a train. Maybe they were traveling by train. I mean, who knows? Is there really a right answer? Yeah, I don't know how they were traveling. But this is definitely the right answer, that Chuck was going 38 miles per hour. And it wasn't by plane, so it must have been maybe a train or a bus or something like that. Okay, well, this is our setup, is keeping in mind that D equals RT can be manipulated into a rational formula, and then noticing that their times were the same, and so we filled in all their information and we got a proportion which we cross-multiplied and resolved. So we're going to try the same thing 2 more times. 76 and 77 are very similar. So I'm going to start us off by drawing some sort of a diagram or a picture to capture all that information. So how about 76? The speed of a stream is 4 miles per hour. So how can we draw that? Here's my stream. And the speed of the stream, I'm just going to draw a long arrow here. I'm going to say that the stream is 4 miles per hour. Is that a fast stream? Like, would you be scared about getting in the water? Maybe not. But then again, 4 miles per hour is pretty fast. This is 4 miles per hour, right? So it's a fairly fast stream. I mean, if you drop something in the stream, like, I don't know, your wallet or money or something that floats, you'd have to really hustle to catch up to it, right? So 4 miles per hour, it's not incredibly fast, but it is fairly fast. Now what? A boat is going to travel 90 miles downstream in the same time that it takes to travel 45 miles upstream. So how can we add that to our picture? So the boat is going to travel 90 miles downstream. So which way is downstream? This way or this way? To the right would be downstream, right? Because we're going with the stream. The stream is helping us along. So starting here, I'm going to show that I'm going to go 90 miles this way. So this was 90 miles. And that's downstream. And then we're going to turn around, and it takes the same time to go 45 miles upstream. And the key thing that they told us so far is that it takes the same amount of time. So the speed of the stream is 4 miles per hour. The boat travels 90 miles downstream in the same time as it takes to go 45 miles upstream. What is the speed of the boat? So we want to solve the speed of the boat. Well, what is the speed of the boat? We don't know what it is, so we should call it x. So right now, the speed of the boat is x. And we need to think about how we're going to solve this thing. What are your thoughts? There's a few more details we could add in. How fast is the boat? Or how fast is the boat moving down the stream total? Since the stream is going 4 miles per hour and the boat is going x miles per hour, how fast is the boat actually moving relative to the ground? Yeah, x plus 4. So this rate is really x plus 4. And what about when it goes upstream? Because it's going x miles per hour, that's the speed of the boat, but the boat is going 4 miles per hour in the opposite direction. So that rate would be x minus 4.
Oh.
So we've got downstream, the boat is going x plus 4 miles per hour, and it goes 90 miles. Upstream, the boat is going x minus 4 miles per hour, and it only goes 45 miles. And we'd like to solve for x, which is just the speed of the boat. Okay, I think we have everything we need now. So what does it say? It says, if a boat travels 90 miles downstream in the same time that it takes to travel upstream, again, we know that our time is equal. So we could say time upstream is the same as the time downstream. That's how we set up the problem, just like the last one. We're saying that those two times are equal to each other. Then what?
So is it gonna be like
Well, let's state the formula first. So what's our formula for time again? Yeah, d over r. So now this is our d over r for upstream, and this is our d over r for downstream. I could write in there real small, like up, up, and down, down. Maybe you can just keep track that on the left-hand side, we're putting information about upstream, and on the right-hand side, we're putting information about downstream. So what do we put in for all of our information? What's the distance upstream? Yeah, 45. And what's the rate upstream? X minus 4. And on the other hand, what's the distance to go downstream? The distance, 90. And then the rate to go downstream? There. Now again, this still makes sense because my rate is faster. So because my rate is faster, I can travel more distance. And here my rate is slower, and so I'm traveling less distance. So putting these things together does make sense. My rate is slower, so I won't be able to cover as much distance. My rate is faster, so I'll cover more distance. Okay, so now how do we solve? We just cross multiply again. I would put parentheses around both of those, and then cross multiply. And then we would have 45 x plus 4 equals 90 x minus 4. Then take your time, distribute, move your variables to the left, move your numbers to the right. Did anyone get 12?
Yes.
Oh, good.
You didn't sound too
You what?
You didn't sound too confident.
Well, you know, I just like to check everybody. All right, so 12 what? 12 miles per hour is what? The speed of the boat. So in other words, if the river stopped and it was just not a river, but just a lake, then the boat would be zipping around at 12 miles per hour. Now, to put all this in context, the speed of the boat, so that's 12 miles per hour. How fast is the boat going downstream? 16 miles per hour. And how fast is the boat going upstream? 8 miles per hour. And in fact, this is kind of interesting. If you plug those numbers into this proportion, so we're saying 45 over 8 miles per hour is the same as 90 over 16 miles per hour. Is that proportion true? This is 45 miles over 8 miles per hour and 90 miles over 16 miles per hour. How do you obviously know that this proportion is true? Yeah, it's just doubled, right? Both of those, the numerator and the denominator, are just twice as big. So that's it. So we can feel confident that we got the right answer. All right, we have one more. Again, I'm going to start us off with just a drawing to kind of capture everything that's happening in the problem. In this one, it's a plane. And the plane is flying 410 miles with the wind and then 310 miles against the wind in the same length of time. So again, the setup is using time as equal. We're saying that the time of these two trips are the same. So if the speed of the wind is 25 miles per hour, what is the speed of the plane in still air? So this is kind of like the river problem. We don't know how fast the plane is going, but we do know how fast the wind is blowing, just like we knew how fast the river was flowing. So I would recommend that we start by drawing something. So we have a plane flying 410 miles with the wind. So here my distance, so this is with the wind. That distance is 410 miles. And then we're going to fly against the wind. And that distance would be 310 miles. Yep. And what are we trying to find? The speed of the plane. So what should we call that? The speed of the plane? Since we don't know what it is, we should call it x. X is just fine. We can call it x. We could call it r if we wanted to stay in keeping with using r for rate, but it's fine either way. So the speed of the plane is x miles per hour. So what's the speed of the plane with the wind? Yeah, x plus 25. And the speed of the plane against the wind? X minus 25. Okay, so I think making this little diagram here, I mean, it's just a very minimal picture, but at least you can look at it and say, okay, this makes sense. Here they're going faster, they cover 410 miles. Here they're going slower, they cover only 310 miles. We're wanting to find the speed of the plane. And the one thing we know is that the time for both trips is the same. We can set it up similarly. But so what should we say? Not time up, time down. What would we say? What would be a nice word that we could use to describe these two trips? Could you say with and against? That seems just fine. So time with the wind and then time against the wind. So again, time is distance over r. And so we plug in all of our information and go ahead and try it, folks. Plug in all of your information and cross multiply and give it a shot.
Because it's things like that. See, because the same as an impact. Then 52%. Yeah, it could be. Yeah.
This one will be plus this is going to become a positive or negative. This one. This.
Yeah, so
So overall.
so it's like so you get and then it's plus, yes. But yeah, always, oh yeah. No, it's always in the first. I know I read some news, so if it's negative. Is it 2020? Is it?
Okay, folks, let's compare answers. So let's see, going with the wind, we went 410 miles, and the rate was x plus 25. And then going against the wind was 310 miles, and the rate against the wind was x minus 25. And again, as you're doing the problem, you might look at that and check to see that it makes sense, right? Because if your rate is faster, you're going more miles. If your rate is slower, you're going less miles. So you can check. Okay, so then we cross multiply. I hope you put parentheses around those first. And we have what? 410 x minus 25 equals 310 x plus 25. All right, so we do lots of distribution. So 410, what's 410 times 25?
Oh, it's
What is it?
10 to 150.
10, 5,
250.
2 5. Ah, okay, 10 to 50. And then 310 times 25? 750? All right. Okay, so then subtracting the 310, what's that? Oh, yeah, that's right, plus. Okay, So then we subtract the 310x. That gives us 100x, and then we add the 10,250. And that gives us what, 18,000? All right, and then dividing off the 100. Did everyone get 180? Okay. Does that make sense for an airplane? I mean, for a little airplane, right? How fast do big airplanes go? Like 500 miles per hour, typically? So this must just be a little, maybe a prop plane or a smaller plane of 180 miles per hour. That's the speed of the plane. Okay, folks, I know my phone just went off, so we have 5 minutes. Let me talk real quick and give you back your quizzes. So first of all, the practice test, here it is up on the board. The practice test, like I said, I put all of these solutions online. So you can go through online and look at all the solutions. You'll notice I crossed out number 12. I won't give you a graphing problem on the test. So I hope you all go home and look up the practice test. I put it on Canvas under announcements. So if you just go to announcements, you can pull up the test. Does anyone have any questions?
That's the practice.
Practice test. Yeah, I put the solutions online. Yeah, I put the solutions online for practice test. Hey, folks. Sorry. Let me say a couple more things, please. A couple more things. So what's due on Thursday? Your practice test, your practice packet. That's what I'm collecting. But definitely go online and look at the solutions for the practice test so you can feel good about those. Okay, does anyone have any questions? Okay, I'm going to pass back your quiz and then you can go.
Oh, yeah, I'm getting confused.
Yeah.
Sorry for that.
And I couldn't figure that out, so I just wanted to I'm able to just turn a fraction into this fraction. I just not figuring it out. And I know you could.
Show me the problem again. Because it's no F debugging. Was there no library?
No, I bought it on Amazon.
Oh,
Yeah.
thank you. Oh, I forgot to put that in the
Yes, I'll do that right after class. I'm going to take some of the problems off right now.
Wait again?